Welcome to Drone Systems and Control course. This particular lecture talks about artificial potential field. In a previous lecture, we discussed about autonomy and automatic systems. In autonomy, we identified one of the complex tasks, which is sense and avoid, in various components of sense and avoid, and we looked at sensor technology, trajectory prediction, conflict resolution, and finally we came to a point. I have a sensor which is able to detect the threat. It is able to identify the conflict region. Once a conflict region has been identified, how do we generate a local path such that I can avoid the conflict and provide safety of it? Here we are going to take an example, one approach which can generate the local path such that I can avoid the conflict as reliable as possible, right? That's artificial potential field. What is the objective? We are going to understand the fundamentals of artificial potential field. We are going to formulate the artificial potential field mathematically for path planning. We are going to apply artificial potential field to global path planning and obstacle avoidance. We also recognize the limitations of artificial potential field based methods. Now let's look at what is artificial potential function. Okay, what is APF? Right, in a short form, APF. Right, a path planning and obstacle avoidance technique inspired by physical potential field. Right. Treat the drone, which is as a charged particle in the field of forces. An attractive force pulls the robots towards the goal. A repulsive force pushes the robot away from the obstacle. Simple idea, right? So one towards a goal, somebody need to attract me. The other one, safety comes into picture. All the obstacles will push the robot away from me. Right? The robot is a charged particle. Here I am using the word robot. It could also be applied for ground robot and aerial robot. Okay, that's why I use the word robot here. What I meant is the drone is a charged particle. Let's say this is a charged particle with all positive charge. All obstacles are looked at as a positive charge. So same charge will repel. The goal is a negative charge, but it will attract the drone towards it. Okay. So when the drone flies, when it comes closer to the obstacle, which is a positive charge, which is repel, so it will push away, and then the goal will attract towards it. Then other forces will also repel and then try to reach the goal without colliding with the obstacles. Right. The negative charges goal, which always attract. The positive charges is the obstacles, which will repel. Okay. The force, the repulsive force decay with respect to distance from the positive charge. Right. That's an idea. Right. What I am going to do, how do I use APF? As very simple, intuitive implementation. Right. It's computationally efficient for real time navigation. It works well in structured and static environment. Right. The moment drone moves in the direction of the resultant force generated by combination of attractive and repulsive potential field. That's an idea I am going to use. Right. So that the drone navigates in the zone of obstacles. Right. Now artificial potential function. Let's define them mathematically to understand. Right. Attractive potential, I call it as U, attractive potential, right? It pulls the drone towards the goal location, right? It's act like a gravitational well centered at the goal. Typically increases with the distance to the goal, right? Encourage the progress in the direction of the destination, right? It pulls towards the destination. It defines the overall direction of the movement, right? The attractive potential does that. Whereas the repulsive potential, if you look at on the other hand, it pushes the drone away from the obstacle. It creates a force wall around the obstacle, right? If you look at the attractive potential, it is more like a gravitational well, whereas the obstacle will form a force wall. Only effective with a certain distance, whereas if you look at an attractive potential, its effect increases with the increasing distance. It facilitates obstacle avoidance characteristics. It's active only within the defined influence zone, whereas attractive potential defines overall direction of the movement. So let's define the attractive potential in mathematical sense. U attractive potential is 1 by 2 K is a constant, Q minus Q goal. Q is the current position of the drone. Q goal is the goal's position where I want to go, or it could be next waypoint where I have to travel, right? That distance between the current position, Euclidean distance between the current position and goal is a factor, right? My attractive potential is proportional to the Euclidean distance, right? It interacts with the repulsive field to form a final navigation path, right? Must balance the repulsive potential to avoid overshooting or collision that we need to take into picture, right? Attractive force is basically derived as a negative gradient of the potential. Okay, what is attractive force? F attractive is negative change in U attractive potential, right? Negative gradient. If you are taking a differentiation of this, right, minus Q attractive, sorry, K constant, Q minus Q goal is what is the force that is present in force acting on the charged particle. Here it's a drone. Now let's look at a repulsive potential, right? U repulsive potential. Remember when I talked about repulsive potential, I mentioned it is only acting on some distance. It's more like a force wall, right? Beyond that distance, the force is not going to act, right? Within the distance, the force is going to act, right? Half, again K repulsive, it's a constant, 1 by d of Q minus 1 by d naught, the whole square. What is d of Q? Distance to the nearest obstacle. If you take an obstacle or the conflict region, what is the distance to the conflict region from the current position of the drone, right? That is d of Q. D naught is the influence radius. If your distance to conflict region is greater than, how close that with respect to d naught, that's a factor will be taken into picture for U prep. If the distance to conflict region is very small, then your repulsive potential will be very high. Okay. If it is closer to the region, it will act. Beyond that region, it will not influence. Okay. If d of Q is greater than d naught, right, then the repulsive force will be 0. Okay. K prep is a repulsion coefficient I am taking into picture. Okay. As a drone approaches the obstacle, the force increases sharply, right? When d of Q tends to 0, here I am assuming that it touches the conflict region, the force acting on it will be increases very sharp, right? The repulsive force is a gradient of the repulsive potential what we are getting. If I take a gradient of this, F repulsive is delta U repulsive of Q, right? So if I am doing that, it always directed away from the obstacle. Remember, this repulsive force is acting away from the obstacle, right? Now let's look at resultant force equation. There are two forces acting on the drone. One is attractive force. The attractive force attracts the drone towards the goal, right? The repulsive force acting on the drone right, which is pushing away from the obstacle, right. The drone's motion is guided by the resultant force, which is derived from the total potential, right. The total potential is sum of attractive potential plus repulsive potential, right. The resultant force is calculated as a negative gradient of total potential. When you take a negative gradient of total potential, the resultant force is nothing but sum of attractive force and repulsive force, right. F of q is the resultant force of the drone acting on the drone at position q is equal to attractive force, that is F attractive at position q plus F repulsive at the position q, right. So let us understand the spatial behavior of APF, and that will help us to interpret how the motion of drone is going to take place, right. It will also provide some kind of intuition how potentials guides the navigation, right. It will also make it easier to debug or understand how to fine tune the parameters in practice, right. You have to provide the D naught, what is the effect of this D naught. If you have an intuition of how this potential fields are working, then you can fine tune these parameters, right. If you provide a tighter, then the maneuver will be aggressive. If you provide it larger, sometimes you may not get the feasible solution also, right. So you need to figure it out what will be the appropriate parameters that you need to choose. The drone follows the path of a gradient descent of potential field, right. That is what we are going to use. Okay, let us visualize, right. So drone is there, is all the repulsive forces will be acting away from the obstacle, whereas the attractive force will be acting towards the goal, and that is a resultant force which is going to act on the drone at any given position. Based on that, the drone is going to navigate from here to all the way to the goal. Okay. Now let us look at how do we combine artificial potential field with navigation. Why we need to integrate APF into navigation. APF provides an intuitive and continuous motion guidance, right. At any given point q, we will get the total potential acting on it. The negative gradients talks about the direction of motion, right. So it just provides an intuitive and continuous guidance which acting on the drone based on the environment. In real world navigation, right, requires a robust algorithm to handle dynamic and complex environment, right. Because the environment is not going to be stationary, it is dynamic, and it is also complex. You will have multiple obstacles, some may be stationary, some may be moving. How do we handle it, right. That is why we need to integrate navigation with respect to potential fields. Integrating APF into navigation make it useful for full navigational stack. Otherwise, we will be talking about point to point. I generate a path based on the map where I know where the obstacles are when I visited last time. But the environment is not static, it is dynamic. The obstacles move, right. How am I going to navigate in that particular map, right. That is where I need this. Artificial potential field provides a smooth, responsive guidance, but must be embedded in the control loop which must close up, right. It works best when we combine the sensor data and we perform the safety checks, and we can integrate possibly with a global planner too, right. The integration transforms artificial potential field from theoretical tool into a full stack navigation for drone or even for other robots in navigation in complex dynamic environment, right. Now look at global path planning with artificial potential field. Now how we can use APF in global path planning, right. The entire environment is known a priori. What does it mean? I know the map. I know the static obstacles and I know the goal. See, one important aspect in all this lecture, the drone knows its position precisely. Where am I is known, that Q is known, right? Not just that, goal position is also known. And if there is a map, right, it's like Google Earth map, right? We have the map which talks about all the obstacles which is known, right? One can use a continuous potential field. He can construct over the whole space. Once he constructs over the whole space, the attractive potential pulls the drone towards the goal. The repulsive potential pushes away from obstacles, right? Then I can use APF as a global path planner. I can plan complete path without real-time sensing. Now, this is what I meant, it's a procedural planning, right? You take care of the terrain. You know the map, you know the terrain. Once you have the terrain, once you know the goal position, once you know the initial position, right, you can plan the path such that the drone take care of the terrain, the static obstacle which is being present. I can use it for that global path planning. I can use this in simulation, mapping, pre-planning of static environment. I can generate a global vector field that always present so that drone can follow. Okay. This is more like a procedural path planning, terrain avoidance aspect of it. But if the terrain changes due to certain things, it will not be able to handle. Okay, that's where you need sensing. The assumption here is the terrain doesn't change. The static obstacles remain same. Then I can use APF as a global path planner and generate a trajectory which will provide safe navigation of the drone from initial position to goal position. What is its limitation? It suffers from local minima, right? Places where the net force is 0, but it's not a goal, right? That problem will come into picture. Sometimes it fails if the map is very complex. If the map is cluttered environment, very cluttered, right? We have a lot of trees, a lot of obstacles being present, then it's very difficult to generate the path, right? Now, I can use it for procedural collision avoidance, right? That's what I meant, global path planning. What I can do is I can use it for local path planning. I have a drone as a sensor. It could be a LiDAR or it could be a radar, it could be a camera. It can detect the obstacle, identify the obstacle as a threat, it predict the trajectory of the threat, it can identify the conflict zone. All this has been done together with the real-time sensor capability. Then I can use artificial potential field to generate the feasible trajectory to avoid the conflict region, right? So, we will talk about how APF can be used for path generation, local path generation. APF is computed only for local around the robot. So, attractive field still guides towards the goal. Goal could be the next waypoint which I am looking at. The repulsive field is built from the sensor detected obstacle nearby. Wherever the conflict zone, there is a repulsive field in the conflict zone. So, I need to generate a trajectory in such that I can avoid the conflict zone. I can do in real time so that even if it's a dynamic obstacle, I can handle it, right? So, how am I going to do? As a APF for local path planning, it's reactive, it's very fast and easy to implement in embedded systems. So, I can do it. The time to compute the trajectory is going to be very small. It's suitable for dynamic environment or unknown maps also. That's what I meant. Earlier one is the procedural collision avoidance. Now what we are talking of is real sense and avoid kind of a problem where sensor is able to identify the conflict zone, right? Once a conflict zone is identified, APF will be able to generate the feasible trajectory in real time and can be implemented in embedded device with ease. We often use this with a global path planner for a goal direction. So we have the terrain, we can use the global path planning and we follow the path. Whenever we sense an obstacle, at that particular point of time, we generate this local path using APF. Right? What's the limitation again? It may get stuck in narrow passages or it will show some oscillatory behavior. Basically, when you have a cluttered environment, you will have a problem. Right? I am talking about a basic artificial potential field. There are hybrid methods are there. They combine artificial potential with bug algorithm, or they combine with a wavepoint or radial field. They bring in all this to overcome these local minima. Right? Now, how do we combine this APF with navigation? Right? What are the key components? We can use it for terrain following. Right? Static map is known. Static obstacles are known. I can use APF to generate a global path planning, right? Or I can use A star, which digit star, which we covered in earlier lectures to generate the global path, right? It can be used to smooth the waypoints also to avoid unknown obstacles. We can use APF for local navigation and control. Basically, the sense and avoid point, non-cooperative obstacle comes into picture. When the conflict zone is being detected, I can use APF to generate the path in real time to navigate, right? I can compute the total potential acting on the robot from repulsive forces coming from a conflict region, attractive force coming from the nearest next waypoint. I can generate the trajectory, smooth trajectory, avoid these dynamic obstacles, right? You can also use it in sensor feedback loop, right? You can continuously update the obstacle map from radar or sensor, LiDAR or camera. Every time I do the threat perception, compute the conflict region and keep updating it in APF based local path planning. I can recalculate the repulsive force and then I can handle dynamic avoidance too. It's always a belief that if you take any sensor, the probability of detection of obstacle is very high when the threat is very close to the sensor, whereas the threat is far away, the uncertainty in detection increases. So if we combine it with the sensor feedback loop, the uncertainty sensing will keep decreasing so that whatever the path you are generating will become easier for you to execute, right? To handle the sensor uncertainty also in that sense, right? Now, there are key components that we have to look at it in integrating this with the navigation. You can use it for velocity or motion command. You can convert the artificial potential vector into velocity command, either linear or angular, depends on 2D or 3D, whatever you want to do. We can convert them into linear angular velocities, right? Or we can just operate in kinematic space. We can just simply look at kinematics of it, assuming that dynamics will be taken care by the inner loops. We only talk about the outer loops, then we can just generate only those commands, right? We can also use for collision checking and safety filters. You can use the safety layer to validate whether the motion generated, APF generated motions. You can override if motion leads to unsafe situations. What are the parameters that we need to tune, right? The balance of goal attraction and obstacle avoidance, that's very important. To ensure smooth, stable collision free navigation, to avoid local minima, avoid oscillations in trajectory or excessive detour. You are moving far away from the goal and coming back, which means you consume more energy, right? That fact also we need to take into picture. That's why we need to tune the parameters. What are the parameters that we need to tune? Attractive gain, K attractive. This controls the strength to pull the drone towards the goal, right? Higher the value, faster the convergence, but risk of overshooting or risk of the drone moving closer to the obstacle is very high. If you put a lower value, the path will be smooth, but the progress will be very slow. Time to reach will be very high. Repulsive gain, it controls the strength of pushing the drone away from the obstacles. If you put very high, you have a strong avoidance, can push the drone into local minima also. The probability that you may not find a path is also very high. Put a low, high risk of near collisions, right, will happen. Which means if there is a wind uncertainty or any other sensor uncertainty, you may collide with the obstacle. So K rep is very crucial. Other factor which influence the trajectory is the influence radius D naught, right? It defines the effective range of the repulsive force from the obstacle, how far the repulsive force is going to act. If you put a larger, right, the drone will start avoiding the obstacle very early and becomes more cautious. If you put smaller, you will see the drone start avoiding the obstacle much later. The progress will also be very small, right? Then you have a distance threshold, the distance to goal below which the attractive force may be reduced, right? The distance to obstacle below which the emergency repulsion kicks in. These thresholds also plays an important role, right? There are some parameters are independent, right? Increasing K rep may require increasing K attract, right? These are kind of coupled. Whereas larger D naught with K rep can cause unnecessarily wider detour, right? What are the strategies? I start with the balance values and simulate. And I can use a grid search or adaptive methods to fine tune these parameters, right? Or I can have a monitoring key metrics. What is the time to reach the goal? How smooth the path is? What is the minimum distance that I have always with respect to obstacle? I can use these metrics to fine tune the parameters. Common pitfalls. Overtuned repulsion means you will stuck in local minima. You will not find a path to reach the goal at all. If you put a weak attractive force, you will keep loitering around instead of reaching the goal. If the D naught is poor, the oscillation will be there. Sometime it will be leads to instability near obstacles, right? Just to give you a notion, give an animation to understand, right? I have different agents. Okay, the drones are moving and there are obstacles, the red ones are obstacles, how the path can be generated, right? I can put a multiple drones and they have to go to the goal, right? They have in a formation, they can change based on the field they have, and they can also avoid each other to reach the goal. Okay. What are the limitations of artificial potential field? You have a local minima problem, right? That's one of the biggest issue. The parameters that what we pick will also leads to get a poor solution, right? So we need to be careful with that. The drone may get stuck, right, in a non-goal location. where the net force is 0. So which means I don't have a path to reach the goal, right? This kind of behavior is very common with the non-concave obstacles or symmetrical layouts comes into picture, right? It's very difficult to say in a real world these kind of scenarios will not happen, right? So you need to know when it can fail so you can work out a strategy. Suppose if the robot gets trapped between two obstacles, right? They equally repelled but there no net movement. Think about it, if the symmetry of obstacles being present, static and dynamic, they get repelled, they get stuck. They get stuck, they stay there for longer time, which means they don't reach the goal. That's going to be a bigger problem. The second bigger problem is narrow passage problem. There is a small space. This happens in a cluttered environment. When you have a cluttered environment, the space available between the conflict regions is going to be small. Then repulsive force is going to dominate in those tight spaces. So the drones will not be able to pass through the narrow corridors due to the strong repulsive forces acting on both the sides. These are quite common problems in a cluttered environment, right? You will have a lot of obstacles, so a lot of narrow passages will be there. It may not be sufficient for the drones to pass through those narrow passages. Other problem comes in oscillation in dynamic environment, right? When you come closer to multiple obstacles, the force vector can fluctuate rapidly and that will lead to zigzag motions, right? And those kind of faster acceleration, deceleration can lead to instability. You also face a problem of no explicit path, right? APF does not plan the complete path in advance. It makes real-time decisions based on the gradients. That's more reactive behavior. It's not suitable for global optimality or constraint satisfaction. It's also very sensitive to the parameters. The performance of APF highly depends on K attractive, K repulsive and D naught. These are the key parameters. They will influence time to reach, minimum distance with respect to the obstacle, right? If you tune these APF with a poor K attractive, K repulsive and D naught, that performance will be poor, which may lead to collisions. APF makes an assumption of static obstacle. Classic APF assumes all these obstacles are static and there is a repulsive force around the static force wall, right? It requires modification and enhancement for a dynamic environment. I'll just give you a scenario, right, where APF gets stuck in local minima, right? A non-goal position where the net force is 0. That what I meant is for a drone at a position Q, the net force Fq is F attractive plus F repulsive, which is equal to 0. Which means the drone start moving even though the goal hasn't reached. You see here I started at this particular point and start moving. Due to the cluttered nature, the resultant force at this position is 0, the drone gets stuck even though my goal position is somewhere on the top right hand side corner. Why it gets stuck? What are the causes? Repulsive forces from surrounding obstacles cancels out the attractive force. Strong repulsion is confined to a local area. Poor tuning of the parameters K rep, K attractive and D naught will also cause that kind of a problem. Obstacle placement near the goal. There are too many obstacles near the goal. There is a likelihood that APF will fail to get the path. Right? What does APF does? APF minimize the scalar potential function which can have a multiple minima. Right? How do we avoid the local minima in APF? You can do the random perturbation. Whenever you get stuck, you can perturb randomly. You can inject a random noise so that the motion just being perturbed, and that perturbation may help you, right? But it's non-deterministic. You may have to. navigation function, use mathematically generated non-minima potential function based on the harmonic functions or Laplace equation, but it will increase the computational complexity. You can have virtual force field with memory. It includes the history of visited positions. It creates a repulsive field at trapped locations to push the drone out. But again, it will increase the storage capacity and computational capacity of path generation. You can also use global local hybrid planning. You can combine A star or Digistar combined with the APF, right, to get the better solution. Or you can do adaptive gain tuning. You can dynamically adjust the attractive repulsive gains to overpower the local traps, right? Or you can always have an escape maneuver whenever you get stuck, right? When you get into the stagnation point, right, you can trigger this predefined escape behavior. Either you can do backtracking or you can do previous path, whatever path you follow, and at the point where the field comes into picture, you take a random direction and then see whether you can escape. In a summary, the artificial potential field, right, we talked about. See, remember, before starting the course, I made the assumption very clear. We have sensor and the sensor is able to see the threat, right? What does it mean? Sense and avoid, right? Sensor has sensing mechanism, able to detect the threat within the zone, continue to detect them so that I have the trajectory, and I have the trajectory prediction mechanism so that I am able to predict the worst case trajectory in local time, right, near field. Based on that, I have a conflict detection mechanisms which identify the conflict region. This part is taken care, right? Once you have the conflict is detected, I use the conflict detection mechanism. Right? The conflict region is known, which means the location of the conflict is known and the region is known, geometry is known. Using the location and geometry, we can create a force field and use the force field to generate the local path, right? So, you have to connect this particular lecture with the previous lecture to understand, right. So, I can use a two type of path planning can be done. One is terrain following. So, where the map is known, static obstacle is known, I can use a artificial potential field to generate the path. Then I can have a sensor based avoidance, that is a very important part, SAA. I have mechanism to detect the conflict region, then I can use artificial potential field to generate the local path. So, what we did, we made those assumptions that those exist, then we did the mathematical modeling of artificial potential functions and we looked at how intuitive this can be integrated with navigation, right, so that the local path can be generated. The drone can move from the initial position to goal position. Again, one of the strongest assumption, the drone has ability to detect its location, means it has a GPS or sensor fusion approaches to detect where my current location Q is, right. Then we talked about tuning of these parameters, how it will influence. We also discussed about limitation of artificial potential field, particularly the local minima. We talked about different mechanisms that one can adopt to avoid the local minima. And we also discussed about the best practices to use APF, right, when to use APF locally, how you can combine the APF with the global planner, and how do we augment the artificial potential field to escape the local minima as strategies, right, which can add into a navigation function such that you can avoid local minima challenges which is present in APF. Thank you. These are some reading assignments, right. Those were it may be a good idea to go through the planning algorithms by Stephen Lavelle, right. Introduction to autonomous robot, right, robot motion planning. These are the very interesting books one can just go through to understand more about various adaptive mechanisms which is being present, which can help you to overcome the local minima and path planning of the robot. See, path planning and navigation is the same whether you do it for a ground and air. The aerial robot has a additional space of additional degree of freedom when you are talking about in navigation space. That's the only thing you need to understand. Okay, thank you.